Black hole entanglement. By simplest. Black holes and quantum entanglement are two of the most intriguing phenomena in modern physics. Black holes, with their intense gravitational pull, warp spacetime in extreme ways, while quantum entanglement involves particles interacting in ways that seem to defy classical physics, remaining mysteriously interconnected even when separated by vast distances. When these two concepts come together, they raise profound questions about the nature of reality, information, and the universe itself. Quantum entanglement occurs when two or more particles become connected in such a way that the state of one particle instantaneously affects the state of the other, no matter the distance between them. This correlation between the particles defies classical intuitions, as changes made to one particle's state are reflected in its entangled partner, even if they are separated by light years. Entanglement is foundational to quantum mechanics, and it has been experimentally verified many times. The phenomenon can be described through Bell's theorem, which shows that no classical theory of local hidden variables can explain the correlations predicted by quantum mechanics. This has led to the idea that quantum mechanics is inherently non-local, in contrast to classical physics. Black holes, regions of spacetime with gravitational forces so intense that nothing, not even light, can escape, present a challenge to our understanding of quantum mechanics. One of the most significant puzzles is the black hole information paradox. According to general relativity, any information that falls into a black hole is lost forever. However, quantum mechanics dictates that information cannot be destroyed, even if it's swallowed by a black hole. This paradox arises because, over time, black holes radiate energy and lose mass via a process known as Hawking radiation. Hawking radiation is theorized to arise from quantum fluctuations near the event horizon, where entangled particle pairs are created. One particle falls into the black hole, while the other escapes as radiation. If the black hole eventually evaporates completely, what happens to the information that was encoded in the particles that fell inside? When particles are entangled and one of them falls into a black hole, what happens to their entanglement? At first glance, it seems like the extreme conditions inside a black hole would break the entanglement, but quantum mechanics suggests that this is not necessarily the case. In fact, some researchers believe that entanglement persists across the event horizon. In this scenario, even though one particle falls into the black hole, it remains entangled with the particle outside. This leads to the idea that black holes themselves could play a role in preserving quantum entanglement. One theory proposes that wormholes, or Einstein-Rosen bridges, may be related to entanglement, a concept known as ER equals EPR. In this theory, when particles are entangled, they are connected by a non-traversable wormhole. If one particle falls into a black hole, the wormhole remains intact, preserving the entanglement despite the spatial separation. The question of what happens to entanglement when particles approach the event horizon has led to new paradoxes, such as the firewall paradox. This stems from the idea proposed by Almheri, Merolf, Polchinski, and Sully, which suggests that if the information paradox is to be resolved, an observer falling into a black hole would encounter a highly energetic firewall at the event horizon. This firewall would destroy any entanglement between particles, violating the no-drama assumption of general relativity. The firewall paradox arises because, under certain conditions, quantum mechanics and general relativity seem to predict mutually exclusive outcomes. Either information is preserved, and a firewall destroys entanglement, or information is lost, and no firewall exists. This remains one of the most hotly debated issues in theoretical physics. Another approach to resolving the paradox of black holes and entanglement comes from the holographic principle, which states that all the information contained within a volume of space can be described by the information on the boundary of that space. In the context of black holes, this means that the information about everything that has fallen into the black hole is encoded on its event horizon. This idea is closely related to ADS/CFT correspondence, a conjecture that relates a gravitational theory in a higher dimensional space to a lower dimensional quantum field theory without gravity on the boundary. This duality offers a framework in which entanglement can be studied in the context of black holes without running into the same paradoxes. In such models, the entanglement entropy of quantum states inside and outside the black hole can be computed, offering insights into the behavior of black hole entropy and the nature of spacetime itself. As black holes evaporate through Hawking radiation, another challenge arises regarding quantum information. If information that falls into the black hole is preserved in the entanglement of Hawking radiation, then the entanglement between the particles inside and outside the black hole must break down over time, leading to a loss of information in the external radiation. However, quantum mechanics suggests that this should not happen. One possible solution is the idea of quantum error correction, where the information that falls into a black hole is not lost but rather scrambled in a way that is reversible. This could mean that the information is not destroyed but instead dispersed in the radiation emitted during the black hole's evaporation. Recent studies suggest that black holes might act like complex quantum computers, scrambling the information inside in a way that is consistent with the rules of quantum mechanics. Black holes are a natural testing ground for ideas about quantum entanglement because they push our understanding of physics to its limits. The interplay between black holes and entanglement brings to light the tensions between general relativity and quantum mechanics, two of the most successful but seemingly incompatible theories in physics. Ongoing research aims to resolve these paradoxes, with theories like holography, quantum error correction, and the ER=EPR conjecture offering new frameworks to explore. We do not yet have a complete theory of quantum gravity. However, the study of entanglement in black holes is pushing the boundaries of our understanding and may ultimately reveal deeper truths about the fabric of the universe. This was an overview of the relationship between black holes and quantum entanglement, covering essential ideas and open questions that physicists continue to investigate. The journey to unify general relativity and quantum mechanics is ongoing, and black holes may hold the key to solving some of the most profound mysteries in modern physics. Thanks for watching. If you liked this video, make sure to subscribe for more.